Hey guys, okay, this is the second part to that video that I made, and I decided we don't need to see my face because you can't see some of the stuff on the screen if my big bald head is there. Now, these are my three graphs. I had to redraw the bottom graph in order to get them all line up. So what are we going to do with these graphs? These graphs tell us about what's going on with the displacement velocity and the acceleration of our spring as it's oscillating back and forth. Now what's cool is that if you line up these three graphs, each of these positions will tell you from, like all, let me put some lines here. If I can make my mouse move in a straight line. Look at how bad I am, guys. Even when I'm not in class. So what happens is, if you line these three graphs up the way I've done, then at each moment in time, you can figure out what's going on with the system, right? What's the velocity, what's the acceleration at each moment in time here, if you line all these dots up. Oh, God, I just can't draw at all, can I? It's just so bad. All right, so when the timer starts, so here's our block, right? Let me reset. Now, we pulled it all the way out, right? So when time starts, we're at 0. Our velocity is at 0. Our displacement is a maximum. Our acceleration is a maximum because it's being pulled in towards that way, towards negative. So it's on the negative end here, right? So that's what I've got here. Okay, I have a negative A, I have a 0 speed, and I have a positive positive displacement. So that is at 0. And then let's play it. And we're going to pause it at, ooh, it's really going fast. All right, we're going to pause it right here at our equilibrium. And what do we got? Well, now we have 0 displacement because it's back to its equilibrium spot. We have max velocity, and we have 0 acceleration. And that's what I should have here. I should have 0 displacement because it's back to the equilibrium. I have max velocity, and I have 0 acceleration. So what I like about this is if I line up these graphs, I know what's going on in each moment in time. Okay, now a lot of times what people will do is that they will say that this spot, and this spot, so here, here, and here, are all at 0. So I can call that 0. This dot, and this dot are all at pi divided by 2. This line represents pi over 2. And then this dot, and this dot, so this line represents pi. And then this line will represent, let's see if I can draw this, 3 pi over 2. And then these 3 dots that are along this line are at 2 pi. And some of you are asking, where the heck did those come from? What in the world's going on there? Well, this spring is oscillating back and forth, right? And so something, what it's doing, let's just watch it, run it, let's go fast. Look at what it's doing. It's going back and forth, back and forth. If I start at a particular spot, if I start at x max, then one cycle, right, which is a repeated part of the motion, one cycle ends at, boom, x max. Okay? So it's just doing things over and over and over again. It's harmonic. This is very similar to if you have something that starts here, I don't know, maybe it moves in a big circle and ends up there again. I'm going to draw a Cartesian coordinate axis here. There we go. God, I just can't draw really dang, can I? So there we go. So if it starts here, that could be my, I don't know, 0. and it goes from here to there, and right here, this would be half, right? All right, all the way to here would be 180. 180 is also called pi. So half of pi would be pi over 2. If it goes all the way down to here, that's 3 pi over 2. And then if it comes all the way back again, that's 360 or 2 pi. Right? So all these things, this and this and this, these are just talking about if we look at this as, as something moving in a circle, right? Yeah. It's the same thing. Okay? So, this spring moving back and forth and us graphing it and getting these little waveforms it's the same thing as moving in a circle, and that's where all these things come from. This would be 0, this would be 90, this would be 180, this would be 270, and this would be 360. Got it? Same thing around here. Okay, so that's where that comes from. Now, let me erase all this. I'm going to keep my graphs. What are we going to have to do with these graphs? What are these graphs going to do to us? Lots of pain, right? Okay, so these graphs are going to tell us what's going on with the spring mass system, and we can come up with equations for these graphs. Okay, I'm going to try a text box here, and I didn't practice this, so I might screw this up. I don't know. Okay, so I can type something. Type something, it says. Oh, I will. Right. So let me type something. Okay, let's see if I can do this. So there's an equation for our displacement graph. So if we have our displacement graph here, there's an equation for this. Displacement is equal to a cosine, and in parentheses, omega t. Okay, that is the equation for this graph. And some of you who are in pre-cal or something, or if you're very mathy, and of course I've told y'all I'm not very mathy, but if you're mathy, then you will see that this curve here is, it's a cosine graph, right? It's some function of x cosine theta. X equals, x equals, go away. This graph is some function of x equals cosine theta, right? So that's why there's cosine here. A stands for the amplitude, right? Would be that maximum. So here again, when you have your spring and it goes all the way out to x max, or all the way down here, it gets squished into negative x max, that would be our amplitude, right? That's a maximum there, okay? Omega t. Omega, what the heck is that? That is rotational velocity. T is time. Okay, interesting. So, what is omega t? Well, you're going to have to look in your notes. Okay, sorry. But omega t is equal to, draw a little arrow, is equal to something called theta. This is a displacement. Why is it omega? I mean, why is it theta? What the heck's going on here? Well, remember, we were just talking about how these graphs are the same thing as something going in a circle, right? So that's why we're using omega t. Because we're talking about something going in a frickin' circle. Yeah. I'm going to erase all that. I shouldn't say things like this, but ultimately, you just need to know this is the equation for the displacement of a spring mass system. Okay? That's a thing. I'm going to try to go back and write some more text. Is there an equation for the velocity? There is. What type of function is this? You mathy people, what type of function? Let me hear you now. All right? Velocity is equal to, this is a negative sine graph. That's the equation for velocity. So this graph, the velocity of our spring mass system is equal to sine. It's a sine function. So omega times a times omega t, right? This will tell you the velocity. And then, what is this stupid thing doing? There we go. Acceleration. There is an equation. What type of graph is this down here? Well, looks very much like a negative cosine graph. For those of you who are, how do I do squared? Let me cheat real fast. Chewy. There we go. I'm not perfect at this yet. Let me put a little squared in here. Squared. That's a 2. Well, this isn't working very well. I'm sorry. Squared. I'll just write it in there for crying out loud. Squared a. There we go. Cosine. Omega t. Oh, look at that. It looks like my handwriting from class. Screw it. Anyway, so the displacement graph has an equation a cosine omega t. The velocity graph has an equation negative omega a sine omega t. And then the acceleration is negative omega squared a cosine omega t. And it looks like a bunch of gobbledygook there. So these are our equations. And you can use these to answer questions. Okay. For instance, I got a question here. So this is an example problem I would have given in class if we were in class, right? And so you have a cart that is oscillating on a spring. So very similar to what we were talking about. If it's something that looks like this could be our cart, and it could be going back and forth, right, on a spring. Okay. And so they give you this equation. This is our displacement equation, right? Because it's cosine. Yeah. There you go. So they say that's our displacement. X is our displacement, cosine. So this in here is omega t, which would make this our A, right? There's the equation. When they tell you when time is this, so when this much time goes by, what is the velocity? What is the A? Okay. And so these would be the equations that you would build, all right, based on velocity, right? Wasn't it sine? Velocity was a sine function, right? So that's why we would build this equation for our velocity. Our acceleration should be a cosine function, yeah? Right? Cosine. I barely wrote it in there. And then the answers that you should get. Now, I'm going to pause it here a second. All right, so you can pause the video here and you can take a look at this. These are the equations that you should get if you use these guys. Okay. And then if we pause it, or you pause it, you can fiddle with it. And then the answers you should get are these guys. These are the answers you should get. There you go. So, there's an example problem. Last but not least, this is something that I put on Canvas, and it looks confusing, and it scares folks. And all it is this chart is trying to summarize what happens, right, at each one of these times. You know, we talked about how basically a spring oscillating back and forth is just like something going in a big circle. So here are all of your, different positions, right? Your displacement is either going to be a maximum or a minimum. Your velocity will either be a maximum or a minimum, excuse me. And so these tables are just trying to help you summarize all of that stuff. I hope this helps. I know it's a lot. If you got to rewatch it, rewatch it. But I appreciate you guys trying this. Thank you so much.